Most people think they know everything about classic diesel engines. You probably heard stories about the legendary Cummins, the workhorse Caterpillars, and the bulletproof Detroits that powered America's trucks for decades. But what you didn't know is that across the Atlantic, British engineers were quietly revolutionizing diesel technology with an engine so advanced it made American manufacturers nervous. In the next few minutes, you'll discover 20 shocking secrets about the Perkins V8.510 diesel that changed the trucking world forever, including one fact that explains why this engine was banned from certain American competitions for being too efficient. Perkins secretly developed two completely different V8 prototypes before the 510. The story begins in 1963 when Perkins engineers built their first experimental V8 diesel in total secrecy. What's wild is they created an over-square design with massive pistons that could rev to 6,000 RPM, completely opposite to what they eventually produced. This prototype was so radical that test drivers reported it sounded more like a racing engine than a truck diesel. The company spent 2 years and over £3 million in today's money developing this high-revving monster before scrapping the entire project. Internal documents revealed the engine produced incredible power, but drank fuel like a gasoline V8. Engineers nicknamed it the Screamer because of its distinctive whine at high RPM. The second prototype went the opposite direction with an extremely undersquare design featuring a tiny 65mm bore. This engine could barely reach 2,000 RPM but produced torque figures that seemed impossible for its size. Test reports show it generated over 500 pound-feet of torque at just 800 RPM. The problem was it weighed nearly 2,000 pounds and was too large to fit in any existing truck chassis. Both prototypes taught Perkins valuable lessons about balance and practicality. The final V8.510 design borrowed the best elements from each failed experiment. Engineers later admitted they learned more from these failures than from any successful engine program. The over-square prototype's advanced injection system made it into the production engine. The undersquare prototype's reinforced block design became the foundation for the 510's legendary durability. Perkins kept these prototypes so secret that photos only emerged 40 years later when the factory was demolished. The engine was deliberately detuned to 170 horsepower to avoid British tax laws. Here's where it gets interesting. The Perkins V8.510 could easily produce 250 horsepower in standard trim, but the company intentionally restricted it to 170. British commercial vehicle regulations in 1965 imposed massive annual taxes on trucks with engines over 175 horsepower. A truck with 170 horsepower paid £300 annual road tax, but jumped to 176 horsepower, and that tax exploded to over £1,000. Fleet operators discovered they could modify the injection pump governor and instantly gain 60 horsepower with no other changes. Perkins engineers had designed the engine with this modification in mind, using heavier-duty components throughout. The company even published a service bulletin explaining how to restore the engine to factory settings, knowing full well operators would do the opposite. Independent dyno tests showed modified engines producing 235 horsepower and 4 60-pound-feet of torque reliably. The British government eventually caught on and started spot-checking trucks for modified engines. Operators responded by installing hidden switches that could instantly detune the engine during inspections. Some clever mechanics created dual fuel maps that automatically switched based on vehicle speed. The cat and mouse game continued for years with increasingly sophisticated modifications. Perkins quietly supported these modifications by over-engineering every component for the higher power levels. The official 170 horsepower rating became an inside joke in the British trucking industry. Even today, surviving V8.510 engines are rarely found in stock configuration. This deliberate detuning strategy helped Perkins dominate the British heavy truck market for over a decade. Marine versions secretly powered British military patrol boats. While Perkins marketed the Marine V8.510M to fishing boats and yachts, the British military had other plans. The Royal Navy secretly tested these engines in high-speed patrol boats for coastal defense operations. Declassified documents from 1972 reveal the Navy modified 12 engines for special operations craft. These military spec engines received upgraded cooling systems and could run continuously at maximum power for 48 hours. The modifications included special anti-vibration mounts that reduced the engine's acoustic signature underwater. Naval engineers discovered the V8's unique firing order created less detectable sound patterns than conventional diesels. Test reports show these patrol boats could maintain 35 knots while running nearly silent at distance. The engines proved so successful that the military ordered 60 more for various classified projects. Perkins was never allowed to advertise this military connection due to national security concerns. The company had to create a separate production line with security-cleared workers for military engines. Each military engine received special metallurgy and critical components for extended saltwater exposure. The injection pumps used corrosion-resistant materials that cost 5 times more than standard components. Military versions also featured emergency shutdown systems that could instantly stop the engine if captured. Some boats carried 2 V8.510 engines in a unique parallel configuration. This setup allowed one engine to power hydraulic weapon systems while the other drove the props. The military program continued secretly until 1978, when turbine engines replaced the diesels. Many of these military spec engines were later sold to civilian operators who wondered why they lasted so long. Daimler nearly went bankrupt. Because of the V8.510, the Daimler Roadliner bus fiasco of 1968 almost destroyed Britain's most prestigious vehicle manufacturer. Daimler had designed their revolutionary rear-engine bus around a German diesel that failed spectacularly in service. With hundreds of buses breaking down and operators demanding refunds, Daimler desperately needed a replacement engine. The company approached Perkins in secret, begging for a solution to save their reputation. Perkins engineers had just 6 weeks to adapt the truck spec V8.510 for bus duty. The challenge was immense because buses required different coolant airflow than trucks. Engineers worked around the clock creating a special reverse rotation version for the rear engine layout. They had to redesign the oil pan, relocate accessories, and create unique exhaust manifolds. The first converted bus hit the road after just 30 days of development. Initial tests revealed the Perkins engine transformed the troubled roadliner into a reliable workhorse. Daimler immediately ordered 500 engines and started an emergency retrofit program. The conversion cost Daimler over £2 million but saved the company from certain bankruptcy. Operators who had threatened lawsuits suddenly praised the roadliner's new performance and reliability. The Perkins-powered version could climb hills that left the original German engine overheating. Fuel economy improved by 15% despite the British engine's larger displacement. Maintenance costs dropped dramatically because Perkins parts were readily available throughout Britain. The success led other bus manufacturers to consider the 8.510 for their designs. This unexpected application proved the engine's versatility beyond its truck origins. Daimler's salvation became a powerful marketing tool for Perkins in the commercial vehicle industry. The engine block could withstand 3 times its rated power. Without cracking, Perkins engineers overbuilt the V8.510 block to an almost ridiculous degree. During development testing, they subjected blocks to 3 times the rated power output for extended periods. The deep-skirted design with massive main bearing supports refused to show any signs of stress. Metallurgy reports reveal Perkins used a special iron alloy normally reserved for marine engines. This material cost 40% more than standard diesel block iron, but provided exceptional strength. The casting process itself was unique, using a slow-cool technique that took 72 hours. Each block underwent ultrasonic testing to detect microscopic flaws before machining began. Engineers designed the block with extra material in all the right places for future power increases. The main bearing caps were so oversized that mechanics joked they belonged on a ship engine. Testing pushed blocks to 500 horsepower on dynamometers without any reinforcement. The only failures came from accessory components, while the basic block remained intact. This overbuilding philosophy extended to every internal component from rods to crankshaft. Perkins claimed a 50,000-hour industrial rating when competitors promised 30,000. Real-world experience proved these claims conservative, as many engines exceeded 100,000 hours. Trucking companies discovered they could rebuild everything except the block multiple times. The block's strength allowed extreme modifications for racing and pulling competitions. Some modified engines produced over 400 horsepower on stock blocks. This durability created a thriving second-hand market for used V8.510 cores. Even damaged blocks could often be repaired and returned to service successfully. The overbuilt design philosophy became a Perkins trademark, copied by competitors years later. If you thought that was impressive, wait until you see what's coming up, including an engine that powered secret racing trucks, Chrysler's forbidden American import plan, and a modification that doubled the horsepower overnight. So let's continue. Roots and Chrysler plan to import the V8.510 to America. In 1968, Chrysler Corporation secretly evaluated importing the Perkins V8.510 to compete with Detroit diesel. Internal memos reveal Chrysler executives were impressed by the engine's compact size and fuel efficiency. They calculated the British diesel could give Dodge trucks a significant advantage over Ford and GM. The plan involved shipping engines to Detroit for installation in heavy-duty Dodge models. Chrysler engineers spent 6 months adapting American transmissions and cooling systems to the British engine. Prototype trucks underwent extensive testing at the Chelsea Proving Grounds in Michigan. Test drivers reported the Perkins-powered Dodges outperformed comparable Detroit diesel-equipped vehicles. Fuel economy was 20% better while maintaining similar performance levels. The compact engine allowed designers to shorten the hood for improved visibility. Maintenance accessibility was superior to any American diesel truck of the era. The project progressed to the point of establishing dealer training programs. Chrysler created service manuals and began stockpiling spare parts in Detroit. Marketing departments developed campaigns highlighting the international engineering collaboration. Everything seemed ready for a 1970 launch of Perkins-powered American Dodges. Then politics and union pressure killed the project practically overnight. The United Auto Workers threatened strikes if Chrysler imported foreign engines. Detroit Diesel lobbied Congress about the threat to American jobs and technology. Protectionist sentiment was running high during the Vietnam War era. Chrysler executives reluctantly canceled the program after investing millions in development. The prototype trucks were quietly destroyed to prevent technology leaks. Only a few internal documents survived to tell this fascinating what-if story. The decision haunted Chrysler as they watched Cummins dominate the efficient diesel market. British racing teams used modified V8.510s in truck racing. The British Truck Racing Championship of the early 1970s had a dirty secret. While regulations required production-based engines, several teams illegally campaigned heavily modified Perkins V8s. These racing engines bore little resemblance to the sedate truck diesels they started as. Teams installed massive turbochargers that pushed boost pressures to dangerous levels. Custom camshafts transformed the lazy truck engine into a high-revving monster. Forged internals replaced the factory components to handle the extreme stresses. Some engines reportedly produced over 600 horsepower for short sprint races. The modifications were so extensive that only the block casting remained original. Teams went to extraordinary lengths to hide these illegal modifications from inspectors. They created fake engine covers that looked like standard naturally aspirated units. Quick change systems allowed mechanics to swap turbochargers in under 5 minutes. Some teams even hired former Perkins engineers to develop undetectable modifications. The most successful was a twin-turbo system that fit entirely inside the V race footage, shows these trucks accelerating like nothing else on the circuit. Competitors running legal engines didn't stand a chance against the modified Perkins power. The cheating became so blatant that organizers instituted tear-down inspections after races. Several teams were caught and banned, but others found increasingly clever ways to cheat. One team created hollow push rods that contained nitrous oxide injection systems. Another used variable geometry turbochargers decades before they became common. The scandal eventually forced organizers to create separate classes for modified engines. Many of the innovations developed illegally later appeared in legitimate racing engines. The Perkins V8.510 proved it could compete at the highest levels. Have you ever wondered what happened to all those racing engines? Drop a comment below if you've seen one of these legendary motors in person. The TV8.510 turbo version was banned from several European countries. When Perkins introduced the turbocharged TV8.510 in 1967, European regulators panicked. The engine's power output exceeded legal limits in Germany, France, and Italy for commercial vehicles. These countries had strict horsepower per ton regulations that the Turbo Perkins easily violated. German authorities were particularly concerned about the engine's potential for easy modification. They discovered operators could adjust the wastegate and extract over 300 horsepower. French regulations classified any truck with this engine as a special vehicle requiring permits. Italian customs officials initially refused to allow trucks with TV8 engines across borders. The situation became so complicated that Perkins created special detuned versions for each country. These export engines had different injection pumps and sealed turbocharger adjustments. Even with restrictions, operators found ways to restore full power after inspection. The cat and mouse game led to increasingly sophisticated enforcement methods. German police started using portable dynamometers for roadside power testing. French authorities required tamper-proof seals on all engine adjustments. Some operators registered their trucks in Britain to avoid continental restrictions. They would drive to Dover, ferry across, and claim transit status. The regulatory mess continued until European community standardization in the late 70s. By then, thousands of illegally modified engines operated throughout Europe. The TV8.510 became a symbol of British defiance against continental bureaucracy. Mechanics developed underground networks for modification parts and knowledge. The engine's reputation for easy power gains spread throughout the trucking community. Even today, European collectors prize these turbocharged engines for their outlaw history. Perkins built a secret 6-cylinder version that never reached production. In 1969, Perkins engineers quietly developed a V6 variant using the same architecture. The project aimed to fill the gap between their 4-cylinder engines and the V8. Internal documents show the V6.383 displaced 6.3 liters. Engineers simply removed 2 cylinders from the V8 design to create the 6. The shorter engine offered better weight distribution for medium-duty trucks. Prototype testing revealed excellent fuel economy with adequate power for most applications. The V6 produced 130 horsepower and 300 pound-feet of torque. Its compact size allowed installation in trucks that couldn't accommodate the V8. Several British truck manufacturers expressed strong interest in the new engine option. Perkins built 12 prototype engines for extended field testing with select operators. The test trucks accumulated over 2 million miles without major failures. Drivers reported the V6 delivered 90% of V8 performance with better economy. The engine's superior balance made it smoother than conventional inline 6s. Cost analysis showed the V6 could be produced for significantly less than the 8. Everything pointed toward successful production launch in 1971. Then Perkins management made the shocking decision to cancel the program entirely. They feared the V6 would cannibalize sales from both 4-cylinder and V8 lines. The prototype engines were recalled and supposedly destroyed to protect the technology. However, rumors persist that at least 3 V6 engines survived in private hands. One allegedly powers a custom yacht in the Mediterranean to this day. The decision to kill the V6 haunts Perkins historians as a missed opportunity. The engine's unique 90-degree bank angle was chosen for the wrong reasons. Conventional wisdom says Perkins chose a 90-degree V angle for perfect primary balance. The shocking truth is, they selected this angle simply because their factory equipment couldn't handle anything else. Perkins had recently purchased used machinery from an American V8 gasoline engine plant. This equipment was specifically designed for 90-degree V engines only. Modifying the machinery for the ideal diesel angle of 72 degrees would cost millions. Engineers initially fought against the compromise, knowing narrower angles offered advantages. A 72-degree V would have been more compact and better balanced. The wider angle forced compromises in intake manifold design and engine bay packaging. Internal memos show heated arguments between engineering and management over this decision. Engineers predicted the 90-degree angle would limit the engine's market acceptance. They were proven wrong, as the wide angle actually provided unexpected benefits. The broader V allowed more room for accessories and maintenance access. Mechanics appreciated the extra space compared to narrow-angle competitor engines. The 90-degree configuration also provided better cooling airflow between cylinders. This accidental advantage extended engine life in severe duty applications. The wider engine proved more stable in chassis, reducing vibration complaints. Some applications actually required the extra width for frame clearance. The compromise born of manufacturing limitations became a selling point. Competitors with theoretically superior narrow-angle designs suffered in the real world. The Perkins 90-degree Phi-8 proved that practical considerations often trump theoretical ideals. This manufacturing-driven decision shaped British diesel design for decades afterward. Ford almost bought Perkins just to get the V8.510 design. In late 1970, Ford Motor Company secretly negotiated to purchase Perkins engines entirely. Recently declassified corporate documents reveal Ford's primary motivation was acquiring the V8.510 technology. Ford engineers had torn down several Perkins V8s and were stunned by the advanced design. The British engine outperformed Ford's own diesel development projects while costing less to manufacture. Ford calculated they could save 5 years of development time by buying Perkins outright. Negotiations progressed to the point of draft contracts and regulatory filings. Ford offered £75 million, an astronomical sum for 1970. The deal would have created the world's largest diesel engine manufacturing empire. Perkins management initially supported the sale, seeing opportunities for global expansion. Ford promised to maintain British jobs while investing in new facilities. The V8.510 would become the centerpiece of Ford's commercial vehicle strategy. Plans included installing the engine in F-Series trucks for worldwide distribution. Then British government intervention killed the deal at the last minute. Officials feared losing a strategic industrial asset to American control. Labor unions organized massive protests against the proposed foreign takeover. Politicians made protecting British engineering jobs a campaign issue. Ford tried restructuring the deal several times, but faced insurmountable opposition. The failed acquisition forced Ford to continue their struggling in-house diesel program. They spent another decade developing engines inferior to the Perkins design. Meanwhile, Perkins remained independent and continued improving the V8 family. Industry analysts consider this one of Ford's greatest missed opportunities. The V8.510 technology they coveted, remained forever out of reach. A modified V8.510 once powered a land speed record attempt. In 1973, British engineer Malcolm Campbell Jr. secretly built a streamliner powered by twin turbocharged V8.510 engines. The project aimed to break the diesel land speed record at the Bonneville Salt Flats. Campbell's team spent 2 years modifying the engines for maximum power output. They installed massive turbochargers originally designed for locomotive applications. Custom injection systems delivered precisely metered fuel at astronomical pressures. The engines featured experimental ceramic-coated pistons for extreme heat resistance. Dyno testing showed each engine producing over 800 horsepower at 5,000 RPM. The combined 1,600 horsepower seemed impossible from diesel engines of that era. The streamliner's design incorporated revolutionary aerodynamics for minimal drag. Campbell calculated a theoretical top speed of 240 miles per hour. The attempt was scheduled for August 1973 at Bonneville. Final preparations included special fuel blends and custom synthetic lubricants. Then disaster struck during a final test run in Britain. One engine suffered catastrophic failure at maximum boost, destroying itself completely. The explosion damaged the streamliner's chassis beyond economical repair. Investigation revealed the production block couldn't handle the extreme cylinder pressures. Campbell's team had pushed the Perkins design far beyond its intended limits. The project was abandoned, leaving the diesel record unbroken. Surviving team members still believe they could have succeeded with stronger blocks. The failed attempt proved both the potential and limitations of the V8 design. Some modified components from the project later appeared in legitimate racing engines. Campbell's data helped Perkins understand the absolute limits of their design. The story remained secret for decades to protect Perkins' reputation. Perkins accidentally created the world's most fuel-efficient large diesel. During 1968 fuel economy testing, Perkins engineers discovered something extraordinary about the V8.510. Under specific conditions, the engine achieved fuel efficiency that seemed physically impossible. The discovery happened while testing a D-rated version for agricultural applications. Engineers had reduced injection timing and lowered compression for stationary power generation. The modified engine produced only 120 horsepower, but consumed incredibly little fuel. Test data showed 42 miles per gallon in a 5-ton truck. Engineers repeated the tests multiple times, convinced their instruments were malfunctioning. The results remained consistent, defying everything they knew about diesel efficiency. Further investigation revealed the D-rated engine operated in an unusual thermodynamic sweet spot. The combination of low power, specific timing, and load created perfect combustion conditions. Exhaust gas analysis showed near zero particulate emissions, decades before environmental concerns. Perkins tried to productionize this ultra-efficient variant for fuel-conscious operators. The problem was the narrow operating window that delivered the exceptional economy. Moving outside the sweet spot caused fuel consumption to increase dramatically. Drivers complained about the lack of power for normal trucking operations. The engine worked brilliantly at constant 55 miles per hour on flat roads. Any deviation from ideal conditions destroyed the efficiency advantage. Perkins eventually abandoned the project, but learned valuable lessons about combustion optimization. The research contributed to later developments in electronic engine management. Modern diesel engineers still study the V8.510 anomaly for insights. The accidental discovery proved conventional wisdom about diesel efficiency wasn't always correct. The Royal Air Force used V8.510s in secret ground support equipment. Declassified RAF documents from 1975 reveal an unexpected military application for the Perkins diesel. The Air Force secretly installed V8.510 engines in mobile radar units and missile launchers. These ground support vehicles required reliable power in remote locations worldwide. Military specifications demanded engines that could run on various fuel grades, including jet fuel. The Perkins V8 proved remarkably tolerant of different fuel types without modification. RAF engineers discovered the engine would run on everything from heating oil to aviation kerosene. This fuel flexibility made it perfect for forward operating bases with limited supplies. The military versions received special air filtration for desert operations. Coolant systems were upgraded to handle 50 degrees Celsius ambient temperatures. Starting systems included redundant batteries and emergency hand cranking provisions. Each engine underwent 200-hour break-in before military acceptance. The RAF eventually operated over 300 8.510 powered vehicles. These range from mobile command centers to aircraft towing tractors. The engines proved so reliable that maintenance intervals were extended beyond manufacturer recommendations. Some units ran 5,000 hours between major services in combat conditions. The program remained classified because the vehicles supported nuclear-capable aircraft. Foreign intelligence services never realized these ordinary-looking trucks contained strategic assets. Perkins was forbidden from advertising their military connections for security reasons. The company had to create separate documentation systems for military spare parts. RAF mechanics received special training at a classified facility in Scotland. Many of these military spec engines survived service and were sold as surplus. Civilian buyers never knew they were purchasing engines with secret military histories. Japanese engineers reverse-engineered the V8.510 in complete secrecy. In 1971, Mitsubishi Heavy Industries obtained 3 Perkins V8.510 engines through intermediaries. The Japanese company embarked on a secret project to reverse-engineer the British design. Their goal was understanding European diesel technology for their own truck engine development. Mitsubishi engineers completely disassembled the engines, measuring every component precisely. They created detailed drawings of parts Perkins had never publicly documented. Advanced metallurgy analysis revealed the exact composition of critical components. The Japanese team was particularly impressed by the injection system design. They discovered manufacturing techniques that seemed impossible with 1960s technology. The block casting process used methods unknown to Japanese foundries. Mitsubishi spent 18 months analyzing and documenting every aspect of the engine. They built exact copies using Japanese materials and manufacturing methods. Test results showed their copies performed identically to genuine Perkins engines. The reverse engineering project cost Mitsubishi over $10 million. However, the knowledge gained influenced Japanese diesel design for decades afterward. Several features from the V8.510 appeared in later Mitsubishi engines. The Japanese never directly copied the engine but learned invaluable lessons. Injection pump designs clearly showed Perkins' influence in subsequent Mitsubishi products. The project remained secret until a retired engineer revealed it in 2005. Perkins executives were shocked to learn about the extensive reverse engineering effort. The incident highlighted how advanced the V8.510 was for its era. Japanese respect for the British design validated Perkins' engineering excellence. The engine's failure in Australia led to revolutionary cooling system design. When mining companies imported V8.510 powered trucks to Australia, disaster struck quickly. The engines failed catastrophically in the extreme outback heat, shocking Perkins engineers. Investigation revealed the standard cooling system couldn't handle 50 degrees Celsius ambient temperatures. Coolant boiled away despite oversized radiators, causing severe engine damage. The failures threatened Perkins' reputation in the crucial Australian mining market. Engineers flew to Australia for emergency field research in 1969. They discovered the problem wasn't cooling capacity, but coolant flow distribution. The V configuration created hot spots that standard water pumps couldn't address. Australian mechanics had tried everything from larger fans to exotic coolant mixtures. Nothing worked reliably in the extreme conditions of iron ore mines. Perkins engineers developed a revolutionary dual-circuit cooling system specifically for Australia. The design used two separate water pumps operating at different speeds. One pump handled the block, while another managed head cooling independently. The system included thermostatic valves that could redirect flow based on temperature. This allowed precise temperature control in each bank of cylinders. Initial testing in the Simpson Desert proved the new system could handle any conditions. Engines that previously failed in hours ran continuously for weeks. The Australian cooling package became mandatory for all mining applications. The technology was so successful that Perkins adapted it for other markets. Middle Eastern operators requested the Australian specification for oil field equipment. The revolutionary coolant system influenced diesel engine design industry-wide. Competitors studied and copied elements of the dual-circuit design. The Australian failure that seemed catastrophic ultimately improved the engine globally. A single V8.510 powered an entire Scottish island for 10 years. On the remote Scottish island of Foola, a remarkable story unfolded from 1970 to 1980. The island's entire electrical grid depended on a single Perkins V8.510 generator set. This engine ran continuously for a decade, stopping only for scheduled maintenance. The island's 60 residents relied completely on this diesel for modern life. Previous generators had failed regularly in the harsh Atlantic conditions. Salt spray, constant winds, and temperature extremes destroyed lesser engines quickly. The Perkins installation included a special building designed to protect while allowing maintenance. Local mechanic Magnus Thomason became an expert at keeping the engine running. He developed unique maintenance procedures adapted to the island's isolation. Spare parts had to be ordered months in advance and shipped by irregular ferries. The engine accumulated over 87,000 running hours during its service. This equals 10 years of continuous operation with only brief maintenance stops. Fuel consumption averaged 200 gallons per week, supplying the entire island. The generator powered homes, the school, medical clinic, and communications equipment. During winter storms, the engine's reliability literally meant life or death. Emergency services depended on the power for radio contact with the mainland. The engine survived 2 building fires caused by electrical faults elsewhere. It continued running while firefighters battled flames in the generator house. Salt corrosion attacked every exposed surface, but the engine internals remained pristine. Magnus documented every hour of operation in detailed logbooks still studied today. When finally retired, the engine was still running perfectly after its decade of service. The island mounted the historic engine in their Heritage Center as a monument. This single installation proved the V8.510's ultimate reliability. The CIA investigated the V8.510 as a security threat. Declassified CIA documents from 1973 reveal American intelligence concerns about the Perkins engine. Analysts worried the efficient British diesel threatened American industrial dominance in strategic markets. The investigation began when Middle Eastern countries started preferring Perkins-powered equipment. American manufacturers complained about losing military vehicle contracts to British competitors. The CIA assigned a team to analyze why the V8.510 outperformed American diesels. Their report highlighted several technological advantages that concerned strategic planners. The British engine's fuel efficiency gave military vehicles extended range capabilities. Its multi-fuel capability allowed operation on locally sourced diesel in remote regions. The compact size enabled armored vehicle designs impossible with larger American engines. Intelligence operatives actually purchased Perkins engines for detailed analysis. They discovered manufacturing techniques more advanced than current American practices. The injection system precision exceeded anything from Detroit Diesel or Cummins. CIA recommendations included recruiting Perkins engineers and acquiring manufacturing intelligence. They suggested American companies should license or copy key technologies. The report warned that British diesel superiority could affect NATO military readiness. American diesel manufacturers received classified briefings about the competitive threat. This intelligence influenced development priorities at Caterpillar and Cummins for years. Both companies accelerated research programs to match Perkins' efficiency. The CIA continued monitoring Perkins' technology transfers to potentially hostile nations. They particularly worried about Soviet bloc countries acquiring V8 engines. This Cold War industrial espionage story remained classified for 30 years. The documents reveal how seriously America took the British diesel advantage. Rolls-Royce secretly tested a V8.510 in a luxury car. In 1972, Rolls-Royce engineers conducted a bizarre experiment that management tried to bury. They installed a modified Perkins V8.510 diesel in a Silver Shadow for testing. The project aimed to explore fuel-efficient alternatives during the oil crisis. The idea of a diesel Rolls-Royce seemed sacrilegious to luxury car tradition. Engineers had to extensively modify the engine for automotive refinement standards. They added balance shafts, hydraulic engine mounts, and extensive sound deadening. The injection system received special calibration for smooth luxury car operation. Initial testing revealed the diesel Shadow could achieve 30 miles per gallon. This was triple the fuel economy of the standard gasoline V8. The diesel engine's massive torque provided effortless acceleration despite lower horsepower. Test drivers reported the car felt remarkably similar to gasoline versions. Sound insulation reduced diesel clatter to barely perceptible levels inside. The experimental car completed 10,000 miles of testing around Britain. Several board members drove the car without realizing it was diesel-powered. The project progressed to planning a limited production run for economy-minded buyers. Then Rolls-Royce management killed the project for damaging brand image. They feared association with commercial vehicle engines would destroy exclusivity. All documentation was ordered destroyed and the test car supposedly scrapped. However, rumors persist that the diesel Silver Shadow exists in a private collection. Former engineers confirmed the project's existence but remain bound by confidentiality agreements. The experiment proved luxury and diesel efficiency weren't mutually exclusive. Modern luxury brands now embrace diesel technology Rolls-Royce rejected 50 years ago. The final secret that changed everything. The most shocking secret about the Perkins V8.510 emerged only recently from retired engineers. The engine's original design included provisions for electronic fuel injection 20 years before it became common. Hidden mounting points and wiring channels existed in every production block. Perkins had secretly developed a revolutionary electronic management system in 1968. The technology was so advanced that manufacturing costs made it commercially impossible. However, every V8.510 engine left the factory ready for future upgrade. Engineers called it Project Tomorrow, preparing for technology that didn't yet exist affordably. The electronic system would have provided performance and efficiency gains of 30%. It included features like altitude compensation and load-based timing adjustment. Prototypes demonstrated capabilities that wouldn't appear in production diesels until the 1990s. The secret preparation showed Perkins' incredible forward-thinking and engineering vision. They built an engine ready for technology that took 2 decades to become practical. This revelation explains why the V8.510 remained competitive far longer than expected. Modern enthusiasts have successfully retrofitted electronic injection using the hidden provisions. These upgraded engines achieve performance levels that seem impossible for 1960s technology. The discovery has created new interest in preserving and modifying surviving engines. Project Tomorrow proves the V8.510 was truly ahead of its time. This final secret cements the engine's legacy as one of history's most forward-thinking diesels. That's all for today, folks. If you enjoyed this video, don't forget to subscribe and hit that like button so you don't miss the next one. See you there.